Well, hello again. Welcome to our journey through complex analysis, and in this little section we're going to briefly look at the complex exponential, trigonometric and hyperbolic functions. And we'll see that these all have lovely analogies in the complex plane, and the properties very, very similar. So how do we begin? Well, we start off with Euler's formula as our motivation, which of course itself is a definition of e to the I theta, and I'm simply going to define e to the z. So I'm thinking of z as x plus iy, so I'm thinking of algebraically peeling off the e to the x, and then I get e to the iy, which I can write as cos y plus I sin y. So I can just symbolically write that down, and then I'm going to take that as my definition now for e to the z. So it's not a proof of this, it's a definition based on just playing with the symbols. It makes a sensible definition. So the real part of e to the z is e to the x cos y, and the imaginary part is e to the x sin y. Now, this is a beautiful definition, but of course, if you think about it for a second, you'll see that because coses and sines are periodic of period 2 pi, then we can see that the complex exponential is now going to be periodic with period 2 pi I. Since if you replace z with z plus 2 pi I, and you simply apply the definition here, then I get e to the x times cos of y plus 2 pi plus I sin y plus 2 pi, and because the trig functions are periodic, period 2 pi gets me back to here, and that's my e to the z. Now that immediately is a very, very interesting fact, that the complex exponential is periodic, but the period is a complex number, it's 2 pi I. And you might like to think about the implications of that in terms of inverses that we'll come to a bit later. So note also, a little exercise here, of course, that the modulus then of e to the z is e to the x. That follows immediately from here. You just take the modulus of this, the square root of the real part squared plus the imaginary part squared, because cos squared plus sine squared is 1. And the modulus of e to the iz is e to the minus y, which I mentioned in passing, but that will be a useful little fact later on. Now it's very easy from the definition to prove the following two results, which I leave you to do. Firstly, that the index laws hold. E to the z plus w is e to the z times e to the w. We sort of hoped that was going to be the case earlier, but it is indeed from this definition that the index laws hold for this exponential function. And e to the z, as you might hope, is an entire function. It's analytic everywhere. And as you might expect, the derivative of e to the z is e to the z. And again, you can check that by simply going back to the definition and applying the formula for the derivative in terms of the real and imaginary parts, and this will come out. That's a nice exercise to do. Little challenge problem to find the image. See what happens to this particular strip here. So we've got x is 1. And y lies between minus pi to pi. I'd like to draw a picture of that little region and see what happens when you map it under w equals e to the z. Now the way you do this, of course, is to map the boundary, even though it's strictly bigger than minus pi. Map the boundary of this region under this, and then you can use continuity to work out what the actual image is, once you know what this function does to the boundary of this region. We note in passing, as I mentioned, because the complex exponential is periodic, then it's not one-to-one, so it won't have a well-defined inverse. This unfortunate fact will need to be re-examined when we come to look at the complex logarithm. And we'll see that as we had to do with the trig functions, which were not one-to-one either, we had to restrict the domain in order to construct inverse trig functions. We're going to have to do a similar thing when it comes to the exponential in order to define a single-valued logarithm, and we'll deal with that in a later section. Just a little example here. We're going to find all solutions to e to the z is 3 plus I root 5. In other words, we're technically going to be finding the logarithm, whatever that means, in the complex plane of this complex number. We're going to do it at this stage from the definition. So I'm going to write z as x plus iy, and I write down the real part of e to the z is e to the x cos y, which is 3, and e to the x sin y is root 5. And if I square these two equations and add, because cos squared y plus sine squared y is 1, I get e to the 2x is 14. Now we're back in the real world again. We're in the real world at this point, so I can just take logarithms of both sides, and I get x is a half log 14. And I'm going to write ln for the real logarithm. I'm going to use the ln notation for the real logarithm. Similarly, back here, if I divide the two equations, then the e to the x's cancel, and I just get tan y is root 5 on 3. And you can see from these equations here that this y is in the first quadrant, so I'm just going to get the inverse. To get y, I'll just be the inverse tan of root 5 on 3. But because the tan is periodic, I'm going to get here plus 2k pi, so when you spin around the inverse tan, you're going to add on 2k pi, and so z then is simply going to be a half log 14 plus I times the inverse tan of root 5 on 3 plus 2k pi, where k is an integer. And that'll give me this complicated looking number here is going to essentially be the logarithm of this complex number. Now, if we now look at another example here, I want to show that f of z is e to the z bar. As soon as you've got conjugates involved, you should be nervous. This one is nowhere differentiable. Even though it's a function of z, it's got a z conjugate in there, and we've seen before z conjugate is not a well-behaved function, and so this one isn't either. And just to convince yourself of that again, you go back to Cauchy-Riemann. So I write down e to the z bar is e to the x minus iy, which I can then use the definition to expand out like this. The real part is just e to the x cos y. The imaginary part is minus e to the x sin y. And if I use Cauchy-Riemann to work out the appropriate partial derivatives, then u sub x is supposed to be v sub y. Well, that's what they are. And the only way these can be equal to each other is if cos y is 0. And that happens when y is n plus a half pi, where n is an integer. So y is pi on 2 plus n pi. But that's a neat way, that's a nice way of writing the general solution of cos y is 0. You say y is n plus a half pi, where n is an integer. Okay, so we get to there. Now I've got to get the other pair of Cauchy-Riemann equations. So u sub y and v has to be minus v sub x. So this equals minus this. That's only going to happen when sine y is 0. And sine y is 0 only happens, the general solution, when y is an integer multiple of pi. Well, hang on, we've got over here y has to be n plus a half pi. And here it's got to be an integer times pi, and you can't be both, so that's impossible. So that means the Cauchy-Riemann equations don't hold anywhere, so e to the z bar is nowhere differentiable. Now, we'd like to then define the trig functions and the hyperbolic functions. So again, motivated by our identities that we've seen in elementary complex numbers, you can see, you will have seen before that if you take e to the iz minus e to the minus iz divided by 2i just gives you sine x, and if you take the sum of these two divided by 2 you get cos x. And so therefore we're simply going to define, we're going to use this to motivate our definition, we're going to define sine z now in terms of the complex exponential. So we're going to define sine z to be e to the I z minus e to the minus I z on 2i, and cos z to be e to the I z plus e to the minus I z over 2. Just be careful, don't forget for the sine you get this extra little I in here that you don't get for the cos. And that defines these functions for complex z. Now, since the exponential is an entire function, I've got linear combinations of the exponentials here, and so that immediately tells me that the trig functions, these complex trig functions, are also entire functions. And again, you can simply differentiate. If you differentiate this with respect to z, then you pick an I up here, so you get I e to the iz plus e to the minus iz times I. The i's cancel and you get cos z. Okay, so you can easily check that the derivative of sine is cos and the derivative of cos is minus sine, as you would expect. That's very nice. And of course, once we have these ones, we can define tan as sine over cos, and we can define the other trigonometric ratios of cosec, sec and cot. Now you can prove algebraically that your favourite trig identity still holds, that cos squared z plus sine squared z is 1. That is, if you take this squared plus this squared and simplify it, everything cancels out and you just get 1. And that's a nice little exercise to do, but I want to mention here without proof the following very, very remarkable result and very useful result, which is part of a more general argument known as analytic continuation. Very, very powerful tool. It says that, and we can't prove it at this stage, but it says that if two entire functions agree on a segment of the real axis, so notice that on the real axis, no matter how small that segment is, then they agree on the whole of the complex plane. That means then, because this Pythagorean identity here, because this holds for z real, it immediately also holds for z complex. So what I can do is I can take the functions f of z is cos squared z plus sine squared z, and I can take the function g of z is 1, and those two functions agree on the whole of the real axis, and therefore by analytic continuation those two functions agree everywhere in the complex plane. Now you see how remarkable that is, because in one single sweep all the usual identities, including double angle results, everything which hold for trigonometric functions of a real variable, automatically hold for functions of a complex variable. And this is good news. We don't need to have to reprove all of those things. They follow instantly once we have this idea of analytic continuation. Now similarly, we're going to define the hyperbolic functions. So sine of x, if x is real, is e to the x minus e to the minus x on 2. So we define sine of z to be e to the z minus e to the minus z on 2. Notice there's no i's in the hyperbolic ones. And the cosh of z is just the average of e to the z and e to the minus z. Now this also, and this is a good little exercise to convince yourself of, that shows you that sine z is equal to minus I sine iz. Now remember that 1 over minus I is I. So another way of saying this is that sine iz is I shine z. Sine iz is I shine z. And similarly you can show from this here that if you take cos of iz, so replace z with iz in the definition for cos, then you get cosh. So sine iz is I shine z and cos iz is cosh z. These are useful facts. And I take it as read that all the other trigonometric functions and the hyperbolic functions can be defined in the obvious way, and that they are analytic on their domains. Now note that some care needs to be taken because functions like sec z and tan z are defined everywhere in the real plane. These are differentiable and continuous everywhere. However, sec z and tan z are not defined when z is k plus a half I pi. So even though the real versions of these are continuous and differentiable everywhere, the complex analogues actually have what we're going to call singularities. They're points where they're not defined at these points here, infinitely many points. However, apart from these functions are analytic everywhere except at this countably infinite number of points. Now, well, having defined sine, we now do what you couldn't do back at high school, and that is we're going to find what complex number has a sine of 2. So that's an interesting question to ask, and that's what we're going to do next. And there are various ways of doing this. You can go back to the exponential definition for sine, and you can do it by that way, and you can solve and so on, but you end up having to get a logarithm at the end because you end up with e to the iz equals something, and you have to take logarithms, and we haven't done logs yet, so I'm going to do this using what you might think of as the expansion method. That is, I'm going to put z as x plus iy, and we're going to use our expansion formulae that still hold in the complex plane. So sine of x plus iy is sine the first cos the second plus cos the first sine the second. And now we use those little results above that the cos of iy is cos y, and the sine of iy is I sine y. So I'll pull the I out the front. We can now equate real and imaginary parts, and that gives me sine of x cos y is 2 and cos x sine y is 0. Call those equations 1 and 2. Now, equation 2 grabs our interest immediately because I've got a product of two things is 0. Now, the only way, well, there's two alternatives here. Either we have y is 0, that makes the sine of 0 is 0, or cos of x is 0. So the only way sine of y can be 0 is if y is 0. These are real now. And cos of x is only 0 when x is n plus a half pi for some integer n. Now, on the other hand, if I plug y equals 0 back into equation 1, the cos of 0 is 1. That gives me sine of x is 2, and now x is real, and that's impossible. We can't solve sine x is 2 if x is real. So in that case, it can't happen. So x must be n plus a half pi. So I copy that here, so therefore x is n plus a half pi. Now, if we plug this back into equation 1 now, then when you work out the sine of n plus a half pi, well, you get plus or minus 1. In fact, you get plus 1 if n is even, minus 1 if n is odd, and you can capture that by writing minus 1 to the n times cos y is 2. Now the cos curve is in the real plane is always bigger or equal to 1, and so if n is odd, this will give me cos y is minus 2, which is no good, so therefore n must be even, and I'm going to write n as 2k, where k is an integer. In that case, then this disappears. I just get cos y is 2, and so again, remember the graph of this one is symmetric. This is an even function, so the solutions of cos y is 2 is y is plus or minus cos inverse 2, which is some number on your calculator. Finally, then, putting all that together, our z is x, which was 2k now plus a half pi, plus iy, that was inverse cos 2. Now, just enjoy that solution for a moment. You see why you were unable to solve sine of x is 2 back in the real world, because the solutions are in fact complex, and moreover not only complex but fairly complicated as well. You get these rather complicated expressions for the sine of z equals 2. The previous example should in fact come as a surprise, because we were solving sine of z equals 2, and there was nothing sacred about the 2. I could have replaced that 2 with a 3 or 4 or 5, and so that means the values of sine z, well, they're certainly bounded when z is real, but I could have replaced the 2 with anything, any real number, or indeed any complex number, and still find solutions. And so that means that the complex sine function is no longer bounded. The modulus of sine of z can be as big as you like. It's no longer a bounded function in the complex plane. This illustrates a very surprising result, which we will be able to prove later in what we're doing, and that is that there are no bounded entire functions except constants. In other words, if I give you a function and I say that it's entire and bounded, then the answer is, well, that's got to be not very interesting. It's just got to be a constant. Now that is very, very different than the situation in the real world. Okay, I finished this little section with just proving this interesting little inequality here, that the modulus of cos squared z plus the modulus of sine squared z is equal to 1. When do we have equality? Well, we certainly have equality. It certainly equals 1 when z is real, and it turns out we'll see that's the only place where you have equality. Now, a couple of ways of doing this. I can prove this one, in fact, really easily just by using the triangle inequality. So I can simply say that the modulus of cos squared z plus the modulus of sine squared z is less, which is equal to 1, is less or equal to the modulus of that plus the modulus of this. And that's it. So you can get that out using the triangle inequality. However, to see when we do have equality, I did it a slightly longer way. So I go back and I expand. So I put z as x plus iy in, and in both of these terms here. Firstly, I pull the square up for the modulus, which you know you can do for these things. And the cos z then is cos the first, cos the second, and cos iy is cos y. And then you get minus sine x, you get sine iy, which is I sine y. And then you do the same thing over here with the sine expansion. Now, to work out the square of the moduli, it's just the sum of the squares of the real and imaginary parts, so you grind through all that. Now, you can take out a common factor of cos squared out of this term and this term. And then when you take out cos squared, you get cos squared plus sine squared is 1. And then I take out a common factor of sine squared out of these two terms, and again I get cos squared plus sine squared is 1. Now, I'm going to use the various ways you can proceed here. I'm just going to use double angles. I leave you to check that cos squared y plus sine squared y is cos 2y, which is just a result you saw when you did hyperbolic functions. This is the double angle formula, if you will, for hyperbolics. And cos is always bigger or equal to 1. And indeed, cos y equals 1 only when you're on the, you've got the variable here is 0, and that's when y is 0. And if y is 0, then z, of course, is real. If you want to play with a little challenge problem, here I give you want to find the modulus of sine of z at z is equal to pi plus I log 2 plus root 5, where this log is the usual real logarithm. So there's a little extra challenge problem to find the modulus of sine z at this complex number. And that is the end of this section.